over. Bypass this.
So you go in here.
Sorry.
Microphone.
Okay.
I think I'm not sure if it's taking this microphone or this microphone right now.
As long as it's a good quality.
As long as just as long as it works on both YouTube and Zoom. Because Zoom probably can't hear me now, right? If I'm not using this. And YouTube probably can't. Okay. And does YouTube work?
Yeah.
Yes? Still works? Okay. Okay. So we can with this. Okay, so let's start. All the materials for the tutorial are on the GitHub. The link should be on Mattermost. So for someone who's not on Mattermost and is on YouTube, this is the link. You will see GitHub repository. It looks like this. If you have followed the installation instruction, you already have it locally, and you hopefully already have started Jupyter Lab, which means that your screen should look something like this. If you don't have it locally, you can always click the launch binder link, these icons, which will start an environment with all the necessities directly in your browser. I think that it's slightly better if you have it locally, because my binder is non-profit organization that has slightly limited bandwidth. And if everyone in the room and online will try to start binder, it may get slowed, or it may not let you in at some point. But since you all got the instructions to set up your environment beforehand, I hope it all works on your side and you are on screen which looks like this. So raise your hand if you do not have your Python instance running at the moment. If you don't know how to do that properly at this spot, just hit the My Binder link on the repository, which will open this kind of interface for you without you having to do anything. And you will be able to follow the whole tutorial directly in your browser. So everyone is set up, everything will work. Okay. So just quick introduction of myself. I am partially academia, partially industry. I am affiliated to Geographic Data Science Lab at the University of Liverpool. I am currently, which is very fresh news, affiliated to Charles University in Prague, where I'm currently based. And I work as a head of data and analytics for the Urban Data Lab, which is a small startup in Zurich, which is focusing on creating insights based on primarily vector data. So everything we will be showing you, we are using on a daily basis there. So I assume we can skip the setup because everything works on your side. If it doesn't, just let me know, but I can't promise I will spend a long time figuring this out for you. So what is GeoPandas, which will be the main focus of today's talk? You may be aware of Pandas, which is a library in Python for working with data frames. So as the name suggests, GeoPandas is a geographic extension of Pandas. And on this colorful diagram, you can essentially see that everything which is index and data is coming from Pandas, and we're just extending it with geometry. So we implement a specific geometry dtype, geometry columns and arrays, and you can have one or more geometry columns on your data frame, but usually one of them being so-called the active geometry. Each of the geoseries can contain any geometry type. It can be point, it can be line string, and then can be polygon, multi-polygon, geometry collection, whatever you fancy, and whatever Geos supports. And each of them has optionally assigned a projection, the coordinate reference system, so we know where exactly on Earth the geometry lies. But since I know that most of you are R users, I will go slowly backwards and introduce Pandas as well. The Pandas developers themselves say that the Pandas is an open source library providing high performance, easy to use data structures and data analysis tools for Python. In practice, it means that they implement two key data structures. One is data frame, and the other is a series. In R, you have data frames built in. In Python, we don't have those, so we need tools like Pandas to supplement those. And it's essentially a tool for management of tabular data. So a series is a one-dimensional vector. It's a column or a row. Since Pandas is a columnar, has a columnar memory layout, series is usually a single column. That's the more efficient way, but you can also access row. Both of these column and row can be accessed as a series. So that's a one-dimensional vector, while data frame is to the two-dimensional array with indices and all the stuff. And I will try to go through that on the actual examples. Pandas is also responsible for a lot of I/O on non-spatial data, so all the CSVs, Excel files, Apache Parquet, all that can be read into Pandas, which means that we can start importing Pandas and start reading some files, so we have something to play with. What I'm going to load here is a data set with the demographic characteristics of Liverpool from the course led by Daniel Basbel in Liverpool. And you can see we can load it directly over the wire, so I wasn't shipping any data on the repository, and everything can be read directly. So we are passing the URL to the CSV, to the read CSV function, and we are saying that use the geographic code as an index, which means that our resulting data frame at the moment looks like this. We have an index with a geographic code. This is a local super output area. It's one of the levels of hierarchy of Office of National Statistics outputs from the census. And we have population based on historical descent in slightly more compressed groups than you would get in the census. So as I said, each column or row is a series, and that can be accessed based on the name, based on location, or based on other filters. So if we, for example, get this column, counting Middle East and Asia population of the descent, we get a series with index and values. So everything in Pandas is extending the underlying representation, which is a NumPy array, which doesn't have any indices. It's just an array of values. And the key point of pandas is that you have this contextual information. What is the column name? What is the row index and things like this. So even if you get the series as one-dimensional vector, you have the values and you have the index next to each other. You can use directly some algebra or turn these columns into Boolean masks. So for example, of all the geographies we have with population of people from Middle East and Asia higher than 500 can give us a Boolean mask. And this Boolean mask, which is exactly the thing which is in here, can be then used to filter the data frame. So if I pass these true, true, false, 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 true, true filter as an indexer that's within the square brackets onto the data frame, I get only those geographies with population higher than 500 on this specific column. And I can also extend this filter by filtering only the columns I'm interested in for some reason. So I have my Boolean mask here. I have a list of specific columns in here, and I can get very small data frame back, which is giving me a subset of what I'm interested in. We can obviously merge columns together or use like do the algebra between columns. The column Africa plus column the Americas gives us a certain value. We can also do sum along one of the axes. In this case, we want sum for each row to get the total population. That gives us a new series, and that new series can be assigned as a new column. So we have our new column in here. I'm going very quickly through the pandas because we have a lot of spatial stuff, and I hope we will get through all of that by the end of the time. Pandas is also implementing some basic plotting capabilities, so we can take our new series, which is called total, and plot it as a histogram. And we see that it's roughly 1500 is the mean of the LSOA. I think that's what the Office of National Statistics is targeting for, but you can also see that these areas are not necessarily all the same in terms of population as the output areas which are below this would be. We can also do scatter plots, and we can, for example, look at the relationship between the population of African descent compared to the one of Middle Eastern Asian. You can see that there seems to be some relationship at this point. We can assume that these people tend to live roughly in the same locations around Liverpool. But so far, we are not able to plot anything on a map because we are in pandas without any geo. So let's go back to GeoPandas. All we've seen here is a pandas data frame and pandas series. GeoPandas wraps all that in a geo data frame, and it implements geo series, which means that this is back the diagram. Index data, that's pandas, as we've seen with LSOAs right now, with the demographics, and we can add geometry next to that. But unlike SF, for example, in R, we are not implementing every single bit we need ourselves in GeoPandas. GeoPandas is designed more as a tool that brings the whole ecosystem together, brings the different pieces we need to do the spatial analysis into a convenient API. So what we need to process geospatial data, we need a way of storing the data, which we just learned is pandas. So all the values, that's covered by pandas. Then we need a way of working with geometries. Since this workshop is on GeoPandas, we're going to talk about vector data only. I'm not going to go into the raster side because it will be slightly different. So on geometry side, we need, in principle, an interface to geos, because that's what most of the open source software is actually relying on. SF is relying on geos, PostGIS is relying on geos. I think that Julia is also using geos to do the processing. I know that there are some attempts to write alternatives to geos, for example, in CUDA, but that's far from being finished. So we essentially need a wrapper for geos geometries, geos engine, which in Python is called Shapely. And that's a library which does only that. only purpose of Shapely is to interface geos and provide all the geometric operations and geometric data types for the rest of the Python ecosystem. The second thing we need to handle are projections. We need to know where on Earth the coordinate actually lies. So it can be slightly easier if you have latitude and longitude. It's very complicated if you have some projected coordinates and you don't know which projection they actually are in. In the open source world, the main engine for this is Proi, which is written in C++, similar to Geos. So we need a wrapper or interface from Python, which is called PyProi. And we also need a way of reading and writing files. And for those of you who went to Jakub's, I think, yesterday's talk, you may see that he showed a diagram which was slightly more complicated than this, but in principle, showed the same thing, that all the I/O of vector data is currently handled, well, most of it is handled by GDAL or GR, which is another C++ library, which can do much more than just reading and writing files. But for those geospatial vector files, we are using Fiona or Pyagrio as Python wrappers around GDAL to get everything into GeoPandas. And all these four parts we need are combined in GeoPandas, and we hope convenient way. So you, as a user, don't have to deal with Shapely yourself. You don't have to deal with projections yourself. You don't have to deal with Fiona to read and write files yourself, because GeoPandas is kind of wrapping that into a package that hides most of it under the hood, and you just do something like GeoPandas read file, and that's all you have to do. So let's do it. Let's import GeoPandas and get another data set from the Geography Data Science course from Liverpool. This time, this is a data set of cities in Spain, which is coming from a paper that was developing a method of delineation of city boundaries. So we see that unlike above, we have one more column with polygon geometries in this case. What I'm gonna do here is that I'm gonna show the cities, let's say with the number of buildings, which is a series, is a Panda series with integer D type. But when we invoke geometry, we have a geometry D type. That is that part that GeoPandas actually implements. All these polygons are Shapely geometries, and we wrap them in a geometry array to get the vectorized access to all of them, and we implement geometry D type. So then we can do all the geometric operations on this geometry, and then we will go through all those due course. Just quickly, since we are reading the file, we can also cover the writing the files. If you have a geodata frame, you can just use the toFile method and write it, for example, to cities geopackage, which creates a file in your home folder in here. GeoPandas is trying to infer the file format from the suffix of it. So if I try to do, for example, GeoJSON, I get the GeoJSON back. And you can see that everything is kind of working as expected. If we don't pass any suffix, we assume that you are trying to save shapefile to a folder. So this is kind of covering the GDAL part. And GDAL is not used in anything else than reading and writing files. And if you, for example, use Apache GeoParquet as your file format, or rely solely on JSONs, you can even read all these without installing GDAL, without handling all those quite heavy dependencies. So let's go through geometries. Let's go through the geoseries and the geometry column. So this is our geometry column. We also already covered the D type. if you get the one of these, we see that this is a shapely geometry polygon. If we don't call type, it also directly gives us a representation of its shape, or we can get the coordinates. You can see that at this point that we have coordinates that surely are not latitudes and longitudes, that we are dealing with some form of projected geodata frame. So without assigned CRS, we don't know where this actually lies on Earth. We can do some spatial operations on that, but we are limited to just planar projected space. But luckily, we do have a CRS attribute, which gives us information that this is actually UTM zone 30N, just suitable for usage in Spain and other places around. And we can quickly see that this CRS object is actually PyProi CRS object. So it's not anything GeoPandas is trying to implement. We just taking that functionality from PyProi and making it available through GeoPandas. So you can directly use that, and you can, for example, ask questions whether the projection is geographic or not. Yeah, we see that this one is not because it's projected. And then we can obviously use this information if you want to reproject geometries from one projection to the other. But where the core of GeoPandas actually lies are the accessors and geometric methods. So I also already mentioned that you can have more than one geometric columns, one geoseries in your geodata frame. One of them is usually called the active, which means that if you try to measure, for example, area of polygons based on geodata frame, not the geoseries directly, it picks the active one. So it just goes through, okay, there is an active geometric column, I will use that one to measure the area. So this gives us a pandas series with float t-type with the values of area measured using Shapely under the hood. And we have already we have assigned it as a column in here. We can also create new geometries based on existing geometries. So for example, if we are interested in getting only the boundary of the polygon to get the line string geometry, we can call boundary, and we can also assign it as a column. So at this point we have two geometry columns in our geodata frame. In a similar way, you could do buffers and other things, or you can do centroids. So if you want to get a centroid, which is a point geometry, to have all polygons, line string, and points in the same geodata frame at the same time, we can do that. Keep in mind that some of these operations, like centroids, require projected coordinates. Otherwise, your measurements will be a bit off, because unlike SF, GeoPandas currently doesn't support spherical geometry. There's an ongoing work which is in sync with Dewey Dunnington, who did the SF implementation for R, but we currently don't have spherical geometry support. So everything you are doing with GeoPandas and Shapely is planar operation. But if you try to do this operation on geographic coordinate system, GeoPandas will warn you that it's probably not a good idea. We can also measure distances. Similar thing, just quickly, we will get the first of the centroids, and then we will measure distances from all the centroids to the first one. Obviously, the first one is 0, everything else is a certain value in meters, and that this is, again, pandas object. What happened here is that we are passing single geometry. We can just quickly check what this is. The single geometry against the whole geoseries of geometries. And GeoPandas is currently using a vectorized engine to do this distance measurement, so the loop doesn't happen on the side of pandas or the side of Python essentially, but it's all on the C level, written in Shapely or PyGeos to be specific, but in the geometry engine. So we sort of eliminated the overhead of Python loops. This is relatively new thing. A couple years ago, it was a for loop in GeoPandas, where we were measuring first against the geometry, second against the geometry. Right now, this is not necessary, and it can give us obviously significant speedups because the geometries right now are not even stored on the Python side, but it's only a pointer to the Geos geometry.
How would you, so you just pass on a series? That's the first one.
If you pass a series, well, what I did right now is that the city centroid, this is a series. If I pass 1 point against series, I get a distance. Point. I get a distance from every single geometry in the series to this point. You can also pass a series in here, in which case the two series gets aligned based on their index, and you get one-to-one distances.
Like a cross combination of 1 point to other points?
Cross combination is not directly implemented. There's an issue open because Christoph, who is doing the benchmarks in the other room, actually pointed this out. We don't have that. You can use apply to kind of do the cross combination, but we don't have this at the moment, and it's probably something that would be more efficient to do on Shapely side, because then it can the kind of the for loop essentially can be written in C.
And reuse the spatial index.
And reuse the spatial index. But right now we don't have this. Yeah. Since the distance we measured is a pandas series, we can use all the pandas functionality we want, like to measure mean, or we can also, for example, plot the histogram as we did above. This all works without us needing to do anything specific. But so far we haven't seen any maps, right? So GeoPandas has two different ways of creating maps. You can create a static map, which has been around for a long time. You just need to get a data frame and call the plot, and it will plot directly the active geometry column. What I'm passing here also is the area. So I wanna get the choropleth map based on the area we just measured above. I also wanted to show me a legend, which is the color button here, and I can probably get rid of this because the resolution is not high enough at the moment. But we also have a new way of plotting maps, which is interactive one, which is using explore function, and is creating a leaflet.js map instead of a static SVG or PNG, which is done using matplotlib in here. The API is fairly similar. Instead of plot, you just call explore. I'm again passing the first passing the column I'm interested in, and I'm turning off legend at the moment. And you can see that this is the data set we are currently working with. Is delineation of cities based on, I think, distances between buildings, and some fancy DB scan algorithm Daniel Basbel was developing. So this is what we are playing with. It's covering the whole kind of Spain off or on and onshore. I'm still talking about active geometry, so we can obviously switch which of the geometries is active. So we can set geometry to centroid, which was created before, and we can look at the centroids. So now we have points. That's not super useful. since we have data set delineating the boundaries, but it can be useful in other cases. And you can also plot both things on the same map. So we now have the centroid on top of the actual polygon we are interested in. I'm gonna set it back because below it's easier to work with actual polygons than centroids. That's what we want to do. But before we will do a bit more, we will have a bit more fun with the Spanish cities. I want to cover another bit, which is called spatial predicates. Spatial predicates tell us what is the spatial relationship between two geometries, whether they are equal, whether they intersect, overlap, whether one is within another one, whether they partially overlap, or I think there's like 7 or 8 of these predicates implemented in GeoPandas and in Shapely. I will use one small toy data set to illustrate these. So GeoPandas comes with a couple of data sets you can essentially play with, or we can illustrate the functionality on what we use in documentation. One of them is a map of countries around the world coming from natural earth in very, very low resolution. And the other one is a data set of point geometry of certain cities coming from the same source. So we can load them. What I'm doing here is that I'm just retrieving the path to the actual file within your GeoPandas installation. So you can see that within my GeoPandas tutorial environment, I have GeoPandas installed in here. It has its data sets, and this is the shapefile I'm loading at the moment. This is how it looks like. We have essentially world, some cities, probably the largest ones. Not sure what is the rule in here. It's not important for this bit. We can extract a small toy example from this. So we can, for example, get Belgium based on the name, and we can get just the geometry of Belgium, which well probably looks something like this. As I was telling, it's very, very low resolution. So if you're from Belgium, I'm sorry, this is not exactly how your country looks like, but it's close enough. From the cities data frame, we can get Paris and Brussels, and we can, for example, make a line string as a connection, direct connection between Paris and Brussels. So here I'm using directly Shapely geometry to create this object, and then I will take it together with Belgium, Paris, and Brussels. This is my Shapely line string right now, and create a geoseries out of it. And this is how it looks like. This is what we have right now. So Belgium, roughly speaking, we have Brussels, we have Paris, and we have connection between the two. So we have point, line string, and polygon geometry. And then we can ask GeoPandas, is Brussels within Belgium? Yes, obviously. It's right here. Does Belgium contains Brussels? Yes. Does Belgium contains Paris? Well, not really. Again, is Paris within Belgium? No, it's not. Does Belgium contains this line connecting Paris and Brussels? No. But do they intersect? Yes, they do intersect. So you can use these predicates to do quick checks on the spatial relationship between the geometries. And there are a couple of other ways how to access this, and we will cover that very, very soon. So far, we've been working with individual geometries. So if I say whether Belgium contains Paris, Belgium is Shapely. So contains is not a GeoPandas feature. It's not a GeoPandas method. It's a method of Shapely polygon. But in exactly the same way, this works on GeoPandas geodata frames. So if we take all the countries, now we have the whole data frame, and ask whether they contain Paris, you will get a lot of falses and one true because Paris is obviously only in France. And we can use this as a filter. So we see that the France is here, and we can quickly look. Okay, it makes sense. We also see that France is quite large country in terms of extent. All these direct checks contains direct predicates, contains intersects. All these are direct because they do not use spatial index under the hood. It's a direct comparison. Does this contain that? You do have an option to use spatial index yourself and query whether Paris is within any of the world countries and get exactly the same result. We considered using spatial index directly in this way an advanced usage because we also have all these implemented within other methods like spatial join or overlay or clip. But you are able to do this, and especially if you want to do a lot of these comparisons, spatial index will give you massive speed up over direct check between one geometry and the other geometry. So probably the main method which is using spatial index is a spatial join. And we can leave this toy example of cities around the world and go back to our Spanish data. And let's assume that I'm interested in which of those cities we have identified in the Spanish data set are within Catalonia. So the first thing I need to have is some data for Catalonia. There is a link to the Catalonian open data portal. We can directly read it with GeoPandas, and it gives us geodata frame with 4 geometries, 4 provinces of Catalonia. And we can check how that look like. Typo here. So yeah, from the whole Spain, we have these 4 regions. So we can try to ask, okay, which of those cities we've seen before fall into Catalonia? And we can also directly say, okay, and which of those provinces they belong to. First thing you would do, which would be like quite smart to do, is to check whether the 2 data frames are actually using the same coordinate reference system. So Catalonia is using WJS84, which means that it's a geographical projection using latitude and longitude as coordinates. Our cities, as we've seen before, are the UTM zone. So if you try to do spatial join between the 2 without any transformation of these geometries, you will essentially get a big mismatch. GeoPandas will warn you about that, will tell you what to do, will tell you that you need to take one of them and reproject using CRS method to the projection of the other. So I will take Catalonia because in this case it's much smaller, so it'll be much faster to do the projection, and we will project one to the projection of the other. And now I can quickly check whether Catalonia CRS equals cities CRS. Yes, so we are ready to go.
Why is it a warning, not an error?
Because in some cases you may have undefined projection on one side.
You would know it, right?
You would know it, yeah. I think that when we are implementing this, there was a discussion on this because originally there wasn't anything. There wasn't a warning, there wasn't an error. GeoPandas just tried to do the spatial join, and it returned empty data frame. When we were doing the warning, it was decided to have a warning there because there was a risk that it would break some behavior. It's most likely wrong to have two projections joining, but we just were we're trying to be cautious not to break existing workflows, because GeoPandas is used by many people in very different and sometimes weird ways, and we're just trying not to raise errors when we don't have to.
Well, you could also argue that by raising error, you would catch errors. That
Yes,
people have overseen, and that if it's not an error, then it's sloppy code.
I'll consider maybe we can change it to the error, but I think that the main reason why it is not an error right now is that there was no check before, and we just wanted to be nice to people who may be doing things in a wrong way.
Actually, we have a similar problem regarding it. So internally, I remember that we use it a kind of custom and projection system.
Mhm.
And the other layer, it was the same projection
Yeah.
system, but we defined it with the ESG code.
Yeah, it may.
And they were equal, but I couldn't match that they are equal. So basically, the warning actually
Yeah.
helped in this case. I know that it was like a
Yeah,
kind of
it may happen.
problem, right?
Yeah.
Because you definitely you should always use the code to define the projection, but I think mostly because you could have some cheaper projection.
Yeah, that's another thing that is worth keeping in mind, is that some of the definition of projections may be not following the standard way. PyPro will work with that, but the assessment of equality will throw false, even though the actual coordinates and actual placement on Earth is the same.
Yes, do you have some recommendation to really try to match this projection for custom projection?
GDAL can do that, yeah, and I think that it's exposed via Fiona CRS module, but I haven't done that myself, so I think that's gonna be the way. I would look either into Fiona CRS module or into PyPro functionality. One of these probably will have some ways of dealing with this. So going back to our SJoin, we can join cities with Catalonia. By default, this is using intersects predicate, but you can also work with other predicates like within, contains. Some of these are even faster than intersects for point and polygon. So right now we have only 65 of the original, I don't know how many of original more than 700 cities. Only 65 of them lie within Catalonia. And what we have here are the columns we have measured and created before on cities data frame, but we also have the columns coming from the Catalonian data set. So we have the province with the name, number, and something. So I'm quickly go to explore. Because of the color map, I'm also changing the tiles to have something less colorful, and we can see that out of the whole Spain, we end up with the set of these polygons, and now they are colored by the province. So this is just a spatial join. Under the hood, it used spatial index, so we hope it should be fast. Again, the result is still pandas data frame in a sense, so we can still use all the pandas functionalities. So if you can, for example, get a sum of cities by the province using the group by function, and work with that in traditional kind of pandas way whenever you don't need geometries. In some cases, we may want to create new geometries based on spatial relationship between existing geometries. These we call overlay operations. And we can create, again, toy example using the Spanish cities and their centroids. And let's assume we are interested in everything which happens within 10 kilometers around the centroid of each of these cities. So we call the buffer on centroids with 10,000 meters, and we get a data set of this sort. And then overlay has several different methods of working. Probably the most common and most simplest one is intersection. So we may want to know what is the intersection between the 10-kilometer buffer around each centroid and the actual geometry of the city boundary. So we call overlay. I'm using here to frame because overlay expects GeoPanda's geodata frame instead of geoseries, which centroids currently are, because it's also joining the attributes. And we will use intersection method on overlay to get the intersection between the two. So you can see that in most cases, the intersection is within the boundaries of the original city boundary, but in some cases, like in Barcelona, where the city boundary is larger, it gets cropped to the buffer. You can also notice that there are different shades of blue. That's because we've seen that we have overlapping polygons in here, and we are preserving all of these. We are not kind of flattening the map at the moment. Another option is to call union, which means that if you have two polygons, you want to kind of merge them if they touch each other. So in terms of overlay, we will end up with a geodata frame which contains the union of all these polygons. But we still have the information of what was there before. So unlike with previous one where we would have only the small polygon in here, we have both, but they are one cut from the other. And we see that the buffer doesn't have any information on it, but the original city boundary has the original information we measured and which came from the data frame. We can also do the difference, find all the parts of the boundaries that are further away than 10 kilometers from each centroid, which is not a lot, but there are some areas like this. And we can also do symmetric difference, which is the last of the overlay predicates we expose with an overlay method. And those are areas which are either within the 10-kilometer buffer or within the boundary, but not within both of these. So you will see that we will have a lot of gaps in these places. So that's the overlay. I have quite well with the time, surprisingly. So we can maybe stop for some questions if you have any questions at the moment. If not, we will go a bit away from GeoPandas to explore the ecosystem. Yeah.
So again, I have a question. So again, this is like you do an operation on pairwise, sort of row-wise and pairs of kilometers, right?
Yes, you use spatial index to get the pairs based on the predicate, and then you do the operation on it. Yeah.
So what if you have like two sets of geometries that are not conform pairs? You have one set.
No, it doesn't matter if they are pairs or not in here. In this case, we do have pairs because we have the centroid on one side and the actual boundary on the other side. But this relationship that one is coming from the other is not included in overlay. So we could have any other geometry in overlay, and it would use spatial index to find the kind of pairs where the predicate matches, whether they do intersect, for example. And then the operation will be done on those pair, on the spatial pair, not the pair which comes from kind of attribute like thing.
Then you end up with an arbitrary set of. I mean, if you would have like the provinces and the cities, and do an intersection.
Then
so you have an N by M, and N geometries and M geometries. They want to get all the intersections.
Yeah, you get a product of that.
So in that sense, that with empty polygons where there are no.
Empties are not included.
Okay, and how do you sort out in which belongs to which?
Okay, let's get some example for that. So okay, so we have the Catalonia as provinces, and we can do the overlay with cities. By default, this is using intersection. So what happens here that, for example, this polygon, which was originally a single polygon, it's now split into based on the different intersection with different region. So you can see that the city ID, which is coming from the city's data frame, is the same, but the province is different. So the operation did the split based on the intersection to make sure that we can do these, for example, properly split them into different subsets.
Based on the attributes, you can sort out where it comes from.
Yes,
Okay.
yes. And then in a similar way, it would work with all the other predicates, but I think that intersection is the most common one. While if we did very similar thing with sjoin, but because it was just a simple spatial join, which was somewhere here, you may notice that this exact polygon a slightly different color because it's there twice, because it matches the predicate for the Barcelona, for the Barcelona province, as well as for the Tarragona province. But what we do with overlay is that we split the geometry and keep only those parts that belong to one or the other. I've seen some other questions somewhere. Yeah.
What is the two frame command doing?
Two frame command takes a series. So buffered centroid is a series and turns it into a data frame with one column, which is the series. Because overlay, as I mentioned, assumes you're merging two geodata frames. So that's what's coming here. Yeah, the provinces are coming from one, and the city ID is coming from the other data frame. So since I have created only a geoseries for this toy example, I'm creating a geodata frame in here to have the proper data type on both sides of the equation. Any other question? Yeah.
Very technical question. If you load data with GDOM, so read well, and then to get it to GEOS, how do you do the conversion? Is that a C library call that does the conversion, or do you put it in well-known binary and then load it?
That's a very technical question.
Like that?
We have, I think there are two different ways at the moment, because for years, GeoPandas has used a library called Fiona to read the files via GDAL. And Fiona will spit the data as a geo interface. So it's like a GeoJSON. And then we load it from there. Then there is a new way of doing that using library called PyOgreo, which is using C to do the conversion between GDAL and GeoS geometries. And since GeoPandas is currently able to work with geometry array with pointers to GeoS geometries, we get this conversion on C and get the pointers back, which is about 10 up to 20 times faster than what's happening with Fiona. And PyOgreo is becoming a default engine for GeoPandas in the future, but you can already use it. So when I was reading something somewhere up here,
I read about the 5G.
Yeah, I'm just gonna show it. So right now this will use Fiona. If you pass engine equals PyGrio, it will give you exactly the same thing, and I will probably. But you see that there is slightly different behavior because PyGrio is still experimental, and it does have an issue when you load the geo package over the wire, which gives you this kind of warning. I think that the current main version doesn't do that anymore, but this is a warning which is coming directly from GDAL, and it's just exposed to the console.
Well, this is a fair one. Right?
It is.
There should be-
Yeah, but Fiona swallows the warning and doesn't give it to us.
Reason I ask because in GeoData frames on Julia,
Mhm.
trying to hopefully get to someday the equivalent or reaching to GeoPandas. We only use GDAL. Basically, in GDAL there are some bindings to geos, of course, building, but it's a limited interface. So we stay in the GDAL point of space,
Mhm.
but never use geos directly, only indirectly via GDAL itself.
Oh.
So it's limited in that sense, but you don't need to do the conversion.
Yeah, but what we are also trying to do at the moment is to minimize our dependency on GDAL, because there's a long history with GeoPandas installation issues, which are mostly related to installing GDAL on Windows. And so PyGrio slightly resolves that because it's much easier to install that on Windows than Fiona. But we are also trying to get rid of hard dependency on GDAL, which I think at the moment already works. So you can use GeoPandas without GDAL installed, but you also want to do the same with PyProi. So you can use GeoPandas only with geos and pandas to minimize the dependencies for people who are not interested in the geo stuff, but only the spatial stuff.
Can it do anything spatial? Without
Well, if you, for example, have a data set capturing the movement of football players around the pitch with a 0 on the one corner, you don't really need to know the projection, and it's all planar operations.
no, of course, if you want to do distances or so.
That's where geos comes in. So as I said, we will depend only on geos and pandas. So geos will take care of distances if they are planar. So
Geos doesn't have to install.
GeoS has to be no, GeoS doesn't, because GDAL has the myriad of dependencies, but GeoS is fairly straightforward library, I think, with minimal dependencies, and we haven't seen issues with GeoS for years on Python side. If I recall, the most issues are with Fiona and some issues are with PyProi, but with GeoS, I don't think I've seen it in recent years. Yeah.
If you have like a really large data set that doesn't fit in memory, for example, posted in a PostGIS database, like millions of rows, can you implement a lazy load?
I'll get there.
Oh,
Yes, you can. Another question before we will move beyond the realm of GeoPandas? Okay. So GeoPandas itself is powerful, but it has essentially a very limited number of functions, because we are trying to keep it lean, trying to keep it focused on exposing geometry operations within Python, within the stable API. But if there are some fancy uses of the spatial data, that usually goes somewhere else. So I will touch a bit on the ecosystem. So I will look into 2 libraries from the Python spatial analysis library called PySal. It's a federation of, at the moment, I believe 21 individual packages in Python. It used to be 1, then it split. Now it's growing in kind of independent way. And that implements everything from basic spatial weight matrices to spatial regression, spatial optimizations, point pattern analysis, asymmetric mapping, regionalization, and stuff like this. I will cover only spatial weights today and spatial autocorrelation a bit. And we will go back to our use case of Liverpool geodemographic data, but this time we will add the spatial part to it. So we can load the geo package with the geometries, which will look something like this. So this is Liverpool within its local authority area and all the local super output areas mapped in here. You can see roughly how large these areas are. And we can go directly into spatial weights. I'm not sure how many of you are familiar with the concept of spatial weights. Some of you, not all of you. So spatial weights are it's an object which is trying to capture spatial relationship between different geometries. The most straightforward way of looking at the spatial weight would be to imagine you have a chessboard and you're trying to know which of the chess, how do you say it? Chess spots, locations are next to which of the other. So you are trying to understand the contiguity between them, or even on this example. So for example, I have this polygon in here, and I want a way of encoding that these polygons are next to each other, next to this one. And spatial weights are a way of doing that. So in the simplest way, it's a Boolean matrix, essentially. It's a sparse matrix that tells you polygon A is next to polygon B, but not next to polygon C. PyCell has a module called libPyCell, which is kind of covering the core functionality of PyCell, core objects, and you can create contiguity spatial weights using the Queen contiguity, which means that the only thing we need between two polygons to consider them next to each other is one shared point. You can also, it's like, again, in chess, queen can move in any direction, and you only need one point to actually move kind of diagonally. You can also have rook contiguity, which needs at least one edge on the side of the polygon to be shared with another to consider them contiguous, to consider them next to each other. Since in this case, we don't really have a lot of polygons that are neighboring on corners, because that's not how the LSOA geometry kind of is created, rook and queen contiguity in this case would be probably equal. But we can go with queen, and we can also use the code of the LSOA, which is this one, which is the same one we already seen above, as a variable to encode the spatial index. So if we measure it, we get back libPyCell object, which doesn't tell us much if you just plot it like this, but we can explore it further. Since I'm using this to use it as a kind of index within the spatial weights, it's also helpful to set it as an index of the data frame itself. So we now have it as an index in here, and we can look into the spatial weights object and say, okay, the one of the geometries, let's say with the one with this index, which is somewhere lost, has weights for that specific location, looks like this. So as I said, it's implemented as a spatial, as a sparse matrix, but working with sparse matrices is efficient in terms of computation, but it's not very friendly. So libpycell is also offering a way of returning all the information as dictionaries. So for the geometry of this geometry code, we see that all these seven geometries are the neighbors, and we also see a value in here. Since we have contiguity, we have value only 1 or 0, which means it is a neighbor or it is not a neighbor, and we omit everything which is not a neighbor in the output. I will probably use the same one in here to get the number of neighbors if you don't want to count these, as I just did. And you can also check if it's more or less than the mean number of neighbors. So in this case, this specific geometry has more neighbors than what the mean would be. And we can also look at what does it mean in map. So we can pick only this one, this geometry we are looking at, and then we can get the neighbors from these and plot both on map. And we say, okay, this is our geometry, and these are our 1, 2, 3, 4, 5, 6, 7 neighbors. So this is what is encoded in the spatial waves matrix. If we are talking about contiguity, but contiguity is not the only way you can work with spatial matrices. Often, for example, if you have point geometry, it may be easier or more useful to say I want to encode which of these geometries are nearest. So let's say 10 nearest neighbors. So we can do k and n weights based on, let's say, k10 in this case. And the result for the same geometry would look like this. So you can see that this polygon is not, that does not touch the geometry. So the contiguity doesn't work here. It will be the second order contiguity. We could work with that. But we have 10 nearest polygons. Or you can say, I want everything within 2 kilometers around my polygon. So you can use distance band and do that. And since I showed that above the values are 1 or 0 in this case, you can also expand it a bit further. And you can turn the value of the weight into, for example, inverse distance between the polygons if we are doing something like 2 kilometers, or use some kernel function to give you the actual weight. How important is the other polygon for my polygon? How to use these things? One of the easiest, straightforward things is to create something called a spatial lag. So we can recall that right now we have these polygons with essentially no interesting information, but above we had the information which is linked to the same geometry, which is encoded as LSOA11CD in here and geographic code in here. So we can merge these two and try to do some spatial lag on the values we have on the pandas data frame. I'm using merge based on attributes in here, directly on GeoPandas geodata frame, and this merge is a pandas merge. So still, we have all the functionality on the spatial side of the thing, but we still have all the stuff that comes with pandas. So if you want to work with datetimes or complex group bys or moving windows, on all these things, it's still available on your GeoPandas geodata frame. So currently we have merged these two. So we have the geometry and we have all the values for each of the geometries. And now we can use the weights we created, and I will be using the queen weights because that's the straightforward thing to do, to calculate a spatial lag. Spatial lag is a simple calculation. It's a mean of values of neighboring polygons if you're talking about Boolean contiguity spatial weight metrics, but it can also be weighted by the actual weight if you have them. And since the computation itself is weighted, we need to turn the values of weights from 1 into row-wise standardized way, because right now, if we use the log spatial method on weights which are all ones, it wouldn't be a mean, but it would be a sum. So if we do the row-wise standardization of weights, you see that each of them gets a portion of the full size, and then if the value from each of polygons encoded by this weight is multiplied within the spatial lag, what we get out of it is going to be mean. But if you have, for example, distance-based spatial weights with inverse distance weighting, you can get a spatial lag which is a bit more fancy, and which includes the information, which weights the information from the closer polygons more than the information from the polygons further away. And right now, what I'm passing into like spatial function from libpy weights module is the spatial weights matrix, the queen weights, and the array of the actual values. So we are passing a panda series of population from Middle East and Asia. There's a very quick calculation, and we get the result. This is a NumPy array, which we can directly assign as a column. Right now, when we have the original values and the lagged values, we can start asking questions, for example, about autocorrelation. Is there a spatial relationship between the location where these people live? Are they clustered within certain locations or not? I think the first easiest way in which we can assess this is to do something called the Moran plot, which is essentially a scatter plot of it's a scatter plot of the original values we got from the dataset and the lag values we just measured. So we know that for each, whether we can look at this and think, okay, does it look that there is a relationship between these two? To me, it does. We can also assess the statistically. We can measure a global Moran's eye to say, okay, there is an indication of spatial autocorrelation, but we can also look into individual polygons and measure the local indicators of spatial autocorrelation, which is implemented in another of the PySL packages, which is called ESDA, which stands for Exploratory Spatial Data Analysis. So what we do, we import the Moran local class in here. And since I showed above that the size of the total population of each LSOA is not equal among all the geometries, it will be better to work with proportion right now. So we can create the column which indicates the proportion instead of the actual raw count, to get it balanced across all the geometries, and then we can compute more on local, passing again the pandas series, in this case the one we just created, encoding the proportion, and the spatial weight matrix. The Moran log will be an ESDA object, which again doesn't tell us much if you print it alone, but we can explore what's inside. To get the traditional output of local indicator of spatial autocorrelation of LISA, which is a map with hot and cold spots, we are interested in two values. One is the quadrant into which each polygon would belong. and we have 4 quadrants. We are trying to capture polygons which have high values by themselves and are surrounded by other polygons with high values. We have on the other side polygons with low values surrounded by other polygons with low values. And then we have the in between. So we have polygons with high values surrounded by polygons with low values. And we have polygons with low values surrounded by polygons with high values. But in most cases, you are interested in high and low clusters. And moranlog.q will give us the labels for all these quadrants, and we will rename them later. But not all these assignments into quadrants are usually statistically significant. So we can get also simulated p-value indicating the significance of each of the results. So you can see that some of them are probably quite significant, some of them very far from that. And we can then use this to filter the output and make the final map. We also have more options, more things to look into. But I'm not gonna go through all of these. We can also retrieve back the contiguity metrics, which was used if you want to, for example, check something, or if you want to use it later in your pipeline. To have a nicer map without 1, 2, 3, 4 values as we get in quadrants in here, I'm gonna rename it into reasonable labels to know what is high, what is low, what is low. And I'm gonna assign the quadrants as a column, which will give me the integers 1, 2, 3, 4. I'm gonna map these labels on top of it to replace the 1, 2, 3, 4s with actual labels. I'm gonna also assign the p-value as another column and then use it as a filter to override the labels with none to get rid of non-significant values. And with this, we can plot the Moran classes. And we see that in this case, in Liverpool, we do have quite interesting clusters. We don't have any of the high-low or low-high. We have only the extremes, and this would say that indicate to us that in the center of Liverpool, within all these areas, we probably have much higher population of Middle Eastern Asian descent than we would get by random chance. And in areas within the low quadrant is the other way. We have much lower population than we would have by random chance. And everything which is kind of gray in here is non-significant. So we cannot say anything about these areas. We don't know whether there is a cluster of people from Middle East and Asia. We can quickly check whether this makes sense if we just plot the proportion of people from Middle East and Asia. And yes, we kind of see that there is a certain tendency to live in city center. I think that in some of these locations, you can see this is the area of University of Liverpool, where a lot of student housing is located. And since University of Liverpool has an agreement with one university in China, which I don't remember by name, there are some shared programs, and quite high population of Chinese students is living nearby university, and this is the hotspots we can kind of see here. In some cases, you may get just the outer these clusters as polygons. So right now we have, I don't know how many, 20, 25 polygons in here, and 15 in here. But we may want to get one, which is just delineating the area of individual cluster. This is back coming to GeoPandas. And what we want to do is that we want to union all the polygons which belong to the same class in principle. GeoPandas has a method which is called dissolve for this, which groups the geometries by their category and calls the union on each of the groups, and also does some aggregation of the other columns. And since it's an extension of GeoPandas group by, you can specify the aggregations using traditional pandas group by aggregation methods. We will go with the default. So we are using this column, which is encoding high, 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 low, 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 and creating one which I will probably rather call quadrant, because clusters is not the best name, which gives us, in this case, two observations in the final dissolved geodata frame, one for all the high classes and one for the low classes. The first one is polygon, the second one is multi-polygon. Rename this, and we can see how the result look like. So this is our original high group of LSOAs, which is now a single polygon, and this is the one representing the low quadrant, which is at this point multi-polygon with all the parts. That's not always what we want. We may want to have each of these blobs as individual part. And again, GeoPandas has a way of doing that, which is called explode. We want to explode the multi-part polygons into its individual parts. And if we index individual parts, I have renamed this. That wasn't the wisest move. We now have all of them as polygons, and we know that all these are coming from the low class, and they originally were a single multi-polygon. So if I now plot this again on a map, you can see that these are now individual parts instead of one big multi-polygon as it's shown here. Okay, there's a bit of small exercise which you can do later. I think it would be interesting to see whether we see similar patterns for other population groups. How does it, to understand how does it also change depending on different spatial weights matrices passed into it. You can place all these things, and then you can, for example, play even with overlay to get a spatial way of understanding which of the areas in Liverpool are, for example, high cluster based on two different spatial weights matrices. You can also do that with attributes, and you can also compare stuff. But since we have last 5 minutes, I'm going to answer the question regarding the data which do not fit the memory, and also possible questions regarding parallelization. So everything we've seen until now was running single core. It was a single thread operation, but our laptops and our cloud clusters usually don't have only a single core, a single thread, and we want to use all the resources we have to do all these computations, especially when our data are larger than 700 polygons, and as we had here. Python ecosystem has a solution for this, which is called Dusk. And Dusk is a framework which provides parallelism and distributed out-of-core computation. It does have one module which is called Dusk data frame, which takes pandas data frames and turns them into a Dusk data frame, which is an object which has many partitions. Let's assume you have a pandas data frame with 1 million rows. You can turn it into a Dusk data frame where each partition has 100,000 rows. And from the perspective of the API, it will all look the same to you. It will be Dusk data frame instead of pandas data frame, but everything, all the methods you are used to or most of them will work as you know them. But if you do some operations on this data frame, the operations will be done in parallel. Each of these partitions will be processed independently, and then Dask will do necessary communication between the workers if you're doing something like means or group bys or stuff like that. And we can build on this with GeoPandas within a project which is called Dask GeoPandas. It essentially does exactly the same thing GeoPandas does on top of Pandas, on top of Dask data frame. So to illustrate what's going on, I'm going to import Dask GeoPandas, and I'm going to take the rather small geodata frame of Liverpool SOAs we've been working with until now, and turn it into a Dask GeoPandas geodata frame with 4 partitions, just for the sake of illustrations. And you can immediately see one difference. We don't see any values in here. The reason behind it is that Dask doesn't know a priori whether your data fit in memory, whether they don't, and it doesn't know what is the most efficient way of processing the whole set of tasks you will give it. So Dask is processing the whole pipeline in a lazy way, which means that what we do in here, for example, if I want to measure length, and then it creates something called a task graph, which, for example, for something as simple as length looks like this. You take the partition 0, you measure the length, and you return partition 0 with the length value. We can also, for example, make a more complicated task graph where we can get the centroid. You can notice that the API for this is exactly the same as we've seen before, but it's not doing the computation as I run the cell. It's creating the task graph like this to process everything as soon as I hit either compute or I want to save it, for example, to Parquet files. So when I do compute, it does the computation and it returns exactly the same result I would expect from GeoPandas, but it does that in 4 different threads in parallel. And you can do the same kind of thing on a cloud cluster on 100 different nodes, and it will still work in a very much similar way as the single core GeoPandas. And in cases when your data don't fit the memory, Dask should be smart enough to dump them to the disk and read them sequentially when it needs them. In practice, it's more complicated than that, obviously, because there's a lot of stuff happening, a lot of things going on, especially when we include the spatial dimension. But for quite a lot of applications, this already works out of the box. The speed up is nearly linear. So if we do a quick benchmark in the last minute of the talk, using 10 million random points, I'm creating 16 partitions in here, and we will do a quick check on the predicate within. So we create a box, like a shapely geometry box, and we will ask each of these random points fall within any within this box. So we have direct comparison because, as I mentioned before, within is not using spatial index by default. So we have essentially an operation which on GeoPandas side takes 344 milliseconds on my laptop with M1 chip, which I'm not entirely sure how many cores it has and uses. And we can do the same stuff on the Dask side, and I'm using time it in here, so it's running multiple times. That's why it was taking a couple of seconds. And we can see that the result is about 76 milliseconds to get exactly the same thing. So that's roughly 4.8 times faster, given this is M1 chip. I don't know how many cores it used, but the speed up is significant. So that's the end of the time. I think we can get a couple of questions if you have them, if you're not super hungry, and we can wrap this up. Thanks.
Thank you. Here are small questions.
I think everyone is hungry. Yep.
How closely does GeoPandas integrate with like raster IO for doing both raster and vector together? And is there good plotting software for plotting both?
I will start from the other question. Yes, good plotting software. If you are interested in interactive visualization, is either IPyLeaflet or HoloViews. So that is able to plot both efficiently at the same time. And the interface between raster and vector is mostly handled by the group of folks who are doing the raster side. So the X-array crowd, which is developing Rio X-array to read the raster files into X-array objects, is also working on a package called GeoCube, which is used for fast rasterization of GeoPandas geodata frames. And there's also raster stats if you want to do the zonal stats. But I think that raster stats had some potential to be faster, given the changes we did recently in GeoPandas. I think it's still doing a simple for loop.
And is there some kind of raster vector integration? You asked that, right? So, if I want to do, let's say, leverage raster cells or polygon.
You would use either GeoCube to get the matching raster with the labels coming from vector, or you would use raster stats if you want to get any touched any touched cell, for example.
Okay.
Okay, let's wrap this up and let's go for lunch. Thank you.